One of the things that you find yourself in need of from time to time is a method of generating a random integer within a specific upper and lower bound. Most of the random number utilities generate pseudo-random numbers. That is, they'll produce the same sequence of random numbers each time they're used. I have a tiny little assembly language program that produces random numbers using the hardware system timer. That way it will produce a different set of numbers every time. Here is the main line to call it. The function is called randint for random integer, and you give it two numbers, the upper and lower bounds of the range of integers from which you wish to have a random number chosen. The numbers can be either positive or negative, and the range is inclusive. That is, either of the numbers that you specify can be chosen as the random number. You'll recognize the basic form of the function. It's just like the two in the previous lesson. It accepts two integers on the stack and uses them to produce a result. It starts out by comparing the two integers and putting them in order. They need to be in order because it's necessary to subtract them to get the size of the range between them, and then the range needs to be a positive number. Either or both of the numbers can be negative. It's just necessary that the range be positive. Then comes a special instruction, RDTSC, which stands for Read Timestamp Counter, loads the 64-bit timestamp counter into the register pair EDX-EAX. EAX contains the low order 32 bits of the counter, which is the one we want. This counter is incremented once every clock cycle, so it is, for all intents and purposes, a random number. It has a couple of drawbacks, but those are fixed by shifting logically 2 bits to the right. First, this is a logical shift, so the sign bit is not extended, which means that if this were originally a negative number, it has now become positive. But there is another reason for this shift. This instruction is what is known as a non-serializing instruction in the hardware, so it could take place earlier or later than its normally scheduled clock time. The result of that is the last 2 bits tend to always be the same, which causes certain numbers in the desired range not to be selected and others to be selected too often. Shifting the last 2 bits out restores the evenness of the distribution of the random numbers. Before we calculate the range of numbers, it is necessary to add 1 to the upper limit. That's because the algorithm we're going to use does not include the upper bound, but this increment puts the upper limit back in the scope of the included values. So now both the lower and upper bound will be included. This subtraction results in the range, the positive distance from the lower bound to the upper bound. Then the same division trick as you've seen earlier takes place. The clock tick value is divided by the range, and the remainder from the division is used as it was in the previous example, giving a random number within the range. Then the lower bound is added to that number to form a number within the range, and we have a random integer inside the requested range. All that's left is to copy the result into the return value register and return to the caller. The programs are compiled and linked the same as they were in the previous lesson. When it runs, it produces random numbers within the desired range. Now, the Great Random Number Consortium will argue with me and say that this is not really a random number. Okay, so it's a fake random number, but basing randomness on a clock seed this way has served me quite well over the years. It's random enough for me.